Okay, let's start again. Okay, the use of rotation matrix. This part we already introduced in the past class, in the first week class. So there is 3 uses of rotation matrix. First, the representation of orientation. It means how to present the orientation of the axis of the coordinate. So the rotation matrix itself represents the orientation. And the second meaning is change the reference frame in which a vector or frame is represented. So the change of reference means when we use the when we use this expression, the reference frame in here was B frame, and by applying the rotation matrix, it becomes the position vector in the reference of A frame. So the change of reference is happened. So by using rotation matrix, we can do this one. And thirdly, the rotation of the vector, rotator vector. About this one, we will explain about more detail in here. So firstly, there is a V vector, and we can represent it in A frame, and also we can represent it in B frame. And here, by using rotation matrix, we can write down this equation. And if we use this equation in here, and in here we input this one, and then it becomes like this. And this one is same as VAX, VAY, VAZ. It means VA vector here. So we can write down like this. This kind of this procedure we already experienced before, and but the same case, but in the different expression method. But this is the same procedure. So in here, the V based on the B frame, and it becomes change the reference frame to A. And let's think about the rotate of the vector. V was in here in A frame, but if we think based on the B frame, we can think like this. B frame, and the vector will be like this, and the V vector in A frame become like this. So this V vector is same V vector, but based on the reference frame, it is shown like this in A frame. It is shown like this in B frame. So in the point of the view, from the point of the view, V is rotated by our matrix. So this is the third meaning in here. So yeah, that's it. So let's think about these examples. This is gimbal style wrist structure. Wrist is this one, wrist. And wrist has 3 degrees of freedom. So we can rotate like this, and it can rotate like this, and it can rotate like this. So it has 3 degrees of freedom, and it can modeled by this kind of gimbal. And gimbal has these 3 link here, here, here. So firstly, there is alpha axis along G axis, and then there is beta axis along Y axis, and there is gamma axis, gamma angle along X axis. And this is zero configuration, and wrist center is always fixed. So even though there is 3 rotation angle, this position is not changed. This point is always same in here. And any rotation or orientation can be parameterized alpha, beta, gamma. So this because the reason I represent this example is this one. In here this one. In R matrix there is 9 parameters, but there is only 3 independent parameters. Because the independent variable is 3, when we represent the orientation, we can parameterize with 3 different angles. So by using alpha, beta, gamma, we can express the rotation matrix R. So at the last class, we call it Euler angle or roll pitch yaw. So this is 3 angle. This 3 angle, it means this parameterized angle. So in this example, R03, what is R03? It means in the reference plane of 0, we express the 3 plane. We express the orientation of the 3 axis, 3 frame. So in here, this in the post multiplication, we multiply in the right side. So by doing this, firstly, we rotate G-axis along G-axis about alpha angle, and then there is changed moving frame. In the moving frame, we use Y-axis and rotate beta angle, and then we change the angle of gamma using the x-axis. So the first rotation matrix like this. So it's z-axis, and this one is y-axis, and then x-axis. So this is relative transformation. Relative transformation, and in the relative transformation, we multiply, post multiply, and we multiply the rotation matrix in the right way. And so the answer was rotate G-axis about alpha angle and Y-axis beta, X-axis gamma. So this is Z Y X Euler angle. And the another expression is, let's rotate X-axis, and the reference frame is S frame. I mean that zero frame. So another representation is absolute transformation. So we always transform based on the zero frame. So firstly, rotate gamma axis along x axis, and then we rotate beta axis along y axis, and then we rotate alpha axis along z axis, and it becomes like this. And this one is same as this one. So this concept was already explained at the last class. So because we choose the reference frame using zero frame, this one is fixed frame. So this one is pre-multiplication, and also this is absolute transformation. So in the absolute transformation, we use pre-multiplication. It means left side multiplication, and firstly x and y and z. So and also this in this expression and also in this expression, the matrix is same. So the resultant rotation matrix is same. So in here we can know the information about roll pitch yaw angle is equal to the Euler angle. Euler angle ZYX Euler angle. So this one is also already explained. So let's think about this problem. The R is SO3. SO3, so this one is rotation matrix. If we want to parameterize the R to ZYX Euler angle, let's find out alpha, beta, gamma. So this means this alpha, beta, gamma is represented by some of the combination of R11, R12, etc., etc. So let's think about this. This three matrix is multiplied like this. And this one is equal to the R11, R12, and this one. So let's find out alpha, beta, gamma. So in here, if we divide C R P beta C gamma, C beta S gamma is equal R33, R32. And this one is erased, and this one become tangent gamma. So if we take the inverse of the gamma, then it becomes R32, R33, like this. And using this kind of calculation, we can also find out alpha and beta. So this is the answer. So this one was about the rotation matrix, and about this class, in this class, you can use the summary video. This one. So you can find out the YouTube video by searching the modern robotics. And about this, I already explained. So let's continue here. Okay. Until now we studied about the rotation matrix, especially about SO3, the concept of SO3. So the key point is R is rotation matrix and R is SO3. So you should memorize this one. And in this time, we will learn about the angular velocity. So angular velocity is the derivative of rotation matrix. So let's learn about this. The velocity is the time rate of change of the position. So when the position is changed, there is time rate. So if it changes fastly, it will have more big velocity. But if it change slowly, it have small velocity. So the velocity is the first derivative of the position. So when we derive the position, it becomes v. So v is time derivative of the position. So the position vector expression here, the xyz is fixed frame, so it is constant. So when we take the time derivative, it becomes p dot, and in here, this value becomes like this. So the position was derivative, in the time derivative in here, here. And then the rotation matrix also can be differentiated. So if we take the time derivative in here, the velocity along x-axis and y-axis, z-axis becomes like this. So because this one is constant, this one becomes like this. So let's find out how to calculate this one. In here, there is x-axis. This one is fixed axis. And there is moving frame in here, the small xyz. And this capital xyz is fixed, and small xyz is a moving frame. And this moving frame is rotating along this angular velocity vector. And this angular velocity is fixed on the fixed frame. So along this axis, like this, okay, this one is x, y, g. This three axis is rotating like this. And when it rotates, it have the rotating vector. So the rotating vector is omega s in here. And we can describe the omega s using the fixed frame and the vector of the omega s like this. So the equation becomes like this. And let's find out this one. In this figure, this one. Okay, we can redraw this part as like this. This one is y, and there is a point. And when it rotates like this point become like this. And here is the theta, and there is pi, theta pi. So you can see it like this. This one is omega s, and this one is y-axis. When it rotates like this, uh, like this. So this A point move like this. So you can think about this one. And the length of the A from A to A dash is delta Y hat. And we can calculate this length using this length multiply the angle of delta phi. And this AC length we can calculate using the sine rule. In here, it look like this: sine theta y vector, size of the y vector, and this is same. And then this delta phi equal omega s, size of the omega s and delta t. So using this one, we can calculate delta t over y delta y, and like this. And this expression is same as omega s cross product y hat when the delta t goes to 0. So the equation of delta y hat dot is omega s vector cross product y hat. So the time derivative of y unit vector can be calculated using the cross product with omega s. So the same calculation can be applied to x-axis and also z-axis. So resultantly, we can write down this equation, and the same expression is merged together, and we can write down here, and then it can transform like this. In here, we find this new concept of skew symmetric matrix. When we calculate the cross product, there is a two method. One is omega s x omega s y omega s z cross product x hat y hat z hat. We can calculate this one when the method we already learned in the high school or the calculus, but to calculate this one effectively, we can transform this vector to skew symmetric matrix. Skew symmetric matrix means when there is a given vector x, x1, x2, x3, the bracket of x vector becomes like this. So we position 0, 0, 0 in here, and x1, x2, x3, x1, x2, x3, and minus, minus, minus. So this one is the skew symmetric matrix of x vector. So when we just use this matrix form, we can calculate this cross product very easily. So this is the same expression. So omega s x is same expression as bracket omega s. So the matrix bracket x is the 3 by 3 skew symmetric matrix representation of x vector. And that is x bracket equal minus x bracket transpose. Because if we transpose this one, 0, 0, 0, this one is 3, but x3, x2, minus x1, x3, x2, x1. And we apply minus, and it becomes like same, it becomes same expression like here. So this one is valid. So the 3 by 3 skew symmetric matrix is called small SOC. Okay, the rotation matrix is large SO3, and this one is 3 by 3 matrix. And if we have some 3 by 1 vector in here, and this one bracket x is small SO3. This one is large SO3, and this one is small SO3. So small SO3 equal to the skew symmetric matrix. And large SO3 is rotation matrix. So this was transformed from here, from vector to matrix. So 3 by 1 vector becomes 3 by 3 matrix, and it becomes skew symmetric matrix by using this bracket. So there is some relationship between large SO3 and small SO3 given any omega, given any omega 3 by 1 vector, omega vector, and rotation matrix large SO3 following always hold. This equation is always hold. This equation is always right. So the rotation matrix and rotation matrix transpose and bracket omega becomes R omega bracket. So this equation is always right. And if there is A cross B, this one is same as A, B equals C. And then always this equation is always right. So this one is the property of skew symmetric matrix. And then let's continue to calculate the angular velocity